Hey guys, before we move on to section 2, can I refer you back to section 1.2? Remember we were talking about how the gradient actually represent the rate here because basically the rate is the change in concentration of the reactant over time. So, but I realized that I forgot to actually include the negative in front here. So rate is equals to the negative of the change in concentration of reactant over the change in time. So why is it that the negative is important? Is because the rate is not just equals to gradient, but the negative of the gradient because of the very fact that rate must always be a positive value. All right, so can you please include the negative sign in front here so that you don't learn the wrong thing? Okay, so then another thing that I want y'all to take note is I realized that when I mentioned A and B, right, I forgot to include this particular equation. So A and B based on this reversible reaction, right, is simply just the reactants, and C and D is just the product. Okay, so you may want to include this one here in order for you to understand what this paragraph is trying to say about A and B and C and D. Okay, so now we can move on to section 2. Section 2, right, notice that in the assessment objective, you're expected to be able to deduce the expression for equilibrium constant in terms of concentration. So if it's concentration, we call it Kc. If it's actually in terms of the partial pressure, we call it Kp. So the treatment of the relationship between Kc and Kp is not required lah. Okay? So what is meant by equilibrium constant? So if you have a reversible reaction here, so where A and B are your reactants and then C and D are your products, so this small little a, b, c, d are just the stoichiometric coefficient for this reaction. So you must remember that when equilibrium, a dynamic equilibrium is attained, right, there will be no further change in the concentration of your reactants and product. So that is the reason why is it that, the graph that we see here, we notice that there is no change in the concentration of reactants and product when equilibrium is reached, right? So, okay, so this would mean that there is a fixed relationship between the equivalent concentration of the reactants and products, and this can be used to express the equivalent constant here. So in other words, right, if I have an equation, so basically the Kc of this particular equation, right, is based on the product of the reaction raised to appropriate power, which is equivalent to the stoichiometric coefficient over the concentration of the reactants raised to the appropriate power, which is dependent on the stoichiometric coefficient. Okay, so this is how we will write the Kc expression. So this is actually quite easy. As long as you have the equation, you have the stoichiometric coefficient, you should be able to write the Kc, which is the equivalent constant expression for any reaction. Okay, so Kc will always be expressed in terms of concentration of the reactants and product at equilibrium. So therefore, the units is mole per dm cubed for concentration, and the units of Kc will depend on the stoichiometric coefficient. Later on, when we look at an exercise, right, we'll go through this. Can at this point of time, you might be wondering, how do we actually, have this particular, come up with this particular so-called expression or formula? Actually, it's quite easy to see it if we understand what is meant by equilibrium. So remember earlier on, I told you that equilibrium is reached when the rate of the forward reaction is equal to the rate of the back reaction. And imagine if this is a single step reaction, so the rate will be equals to rate constant F multiplied by concentration of A and B raised to the appropriate order of reaction, let's say A and B here, and then rate of barrel reaction would be Kb times concentration of C raised to the power of C, and then D raised to the coefficient of D. So this is actually only true if, let's say, this is a single step reaction. Okay, so imagine this is a single step reaction. All right, so therefore, if I were to manipulate with this particular equation here, what you notice is that I can bring Kf and Kb to one side. Okay, and therefore I have C, D, A, and B. Can you see that? All right, so this is how we we'll look at it. And in fact, Kc, right, is simply just a ratio of the rate constant of the for reaction over the rate constant of the reaction. So this K here represents the rate constant. And so that's how we actually come up with this expression. So do you see how this is being derived? Okay. Do you really need to know how to derive? Don't need lah. So actually what you need is, you just need to be able to write the Kc expression given the equation. Okay? Okay, so for equivalent constant Kp, right? So you must remember, this is what you learn in the gaseous state topic, where the partial pressure is simply just the mole fraction multiplied by the total pressure. And we can also calculate partial pressure as long as we assume that it is an ideal gas, and then we have the number of moles of the gas. We can use PV equals nRT. So you realize that partial pressure is proportional to the concentration at constant temperature. Okay, and then your Dalton's law also say that the total pressure is simply the sum of the partial pressure of all the gases in the system itself. Okay, so from this you can tell that the partial pressure of a gas is kind of like proportional to its concentration. And usually, right, if we have a gaseous system, right, it is actually easier to measure the partial pressure rather than the concentration. So that's why instead of expressing it as Kc, we will use Kp. So you must always remember Kc, the C here represent concentration, whereas Kp, the P here represent the pressure, all right, of the gases. Can? So basically, Kp is the equivalent constant for a reaction in which we actually use the equivalent partial pressure of the respective reactants and product in the measurements. So the units of Kp is also dependent on the stoichiometric coefficient of the reactants and products. Okay, so you see the difference, right? So basically Kp, right, if I have a system where these are all gaseous reactants and product, so what I'm trying to write now in terms of my expression for Kp is all in terms of partial pressure. So it will be partial pressure of C raised to the stoichiometric coefficient of C multiplied by the partial pressure of D, which is my product, raised to the stoichiometric coefficient, over the partial pressure of my reactant A raised to the stoichiometric coefficient, as well as the partial pressure of B, which is a reactant, raised to the appropriate stoichiometric coefficient. So you must always remember that it's always the product on top over the reactant. Okay? So certain important points about Kc and Kp for you all to take note is that these are all considered as a constant. So it is a constant at a constant temperature. So it will not change when there's a change in concentration, pressure, or catalyst. Can? So it only changes with temperature. In other words, you may want to say that Kc and Kp only changes with temperature. So Kc and Kp can be written for all reversible reaction. Kc can be written for all reversible reaction, but Kp can only be written when there is actually gaseous reactants and products. Can? And the value of Kc and Kp for reaction is the reciprocal of the value of Kc or Kp for its reverse reaction. So what I'm trying to say is that if you were to look at this particular reaction here, so if I were to write Kp, right, so remember Kp is always product. This is the product. This is the reactant. So, and you raise it to the appropriate power, and because you are talking about Kp, you use partial pressure and partial pressure of O2. So this one, the power is 1 because you only have 1 O2. Then multiply partial pressure of SO2. This is 2, that's why I've raised to the power of 2 over the reactant here. So your reactant is SO3. So partial pressure of SO3 raised to the power of 2. So this is how you write. So the units of Kp in this case will be equals to Pascal, because you imagine that you are measuring your partial pressure in terms of Pascal. So if you think about it, you have Pascal, then Pascal squared over Pascal squared, right? So these two cancel off. That's why the net unit is Pascal. So now if I were to look at the reverse reaction would be when you have SO2 and O2 reacting to give you SO3. So you realize that now your product, this is your product and this is your reactant. Okay, so it is now PSO3 to the power of 2, and your reactant will be PO2 multiplied by PSO2 raised to the power of 2 here. So you realize that this expression, right, is exactly the reciprocal of your earlier reaction here. Okay, so that's what we meant by reciprocal. Okay, so and the units will be just the reciprocal of it. Okay. So you must know that the magnitude of the value, right, the value of Kc or Kp, right, will only give you an indication of the extent of the reaction. So it tells you how far the reaction goes to completion. Okay, so you can tell, so in other words, it tells you how far it goes to completion, but it doesn't tell you, all right, so but it has no indication of the rate of the reaction. So it doesn't tell you how long it takes for the reaction to reach that state of equilibrium. Okay, so anything about rate you cannot deduce from the value of Kc or Kp. Okay. So when the Kc value is large, so large in terms of magnitude, like 10 to the power of 8, anything that is more than 1, so anything that is more than 1, you'll know that actually what it means is that the position equilibrium lies more on the right hand side. So in other words, your proportion of your product is higher than the proportion of the reactant. That's why it's greater than 1. Okay, so it also means that the reaction favors the formation of the product. So it also means that the reaction goes to near completion. Okay, so but if the Kc value is small, the position of equilibrium lies more on the left hand side. So what it also means is that you actually have a higher proportion of reactants. So if you look at Kc is always about product over reactants, right? So that means you have a higher proportion of reactants when your Kc value is small. Okay, so in magnitude of minus something, so that also means that the forward reaction is not favored, and it does not proceed to a great extent, appreciable extent. Okay, so that's what it means here. So if the reaction proceeds in a single step, right, so the Kc can also be considered as the ratio of the rate constant, where Kc is simply just the ratio of Kf over Kb. So this K here represents the rate constant. Okay, so in other words, this is taken from your appendix. So this is what I mentioned just now. So this is actually the same as what I have written in green here just now. So if it's a single step reaction, as I said, the rate of the forward reaction is equals to rate of back reaction when you reach a state of dynamic equilibrium. So therefore, when you take the ratio, can you see that this is equals to Kc? Yeah, so Kc is simply just the rate constant of the forward reaction over rate constant of the back reaction. Okay, and that's how we write the expression as the product raised to the power according to the stoichiometric coefficient over the products of the concentration of the reactants raised to the appropriate stoichiometric coefficient. Okay, so you may also want to take a note for yourself. This is actually something extra, that since Kc is simply the ratio of the rate constant of forward and back reaction, and you will have learned before that this is the rate constant. So the rate constant, right, if you look at the Arrhenius equation, although this is not in the syllabus, but knowing the Arrhenius equation, you can tell that how the rate constant is dependent on the temperature. Right, so you see that it is dependent on temperature. So this is also the reason why is it that when we say that the rate constant for both forward and back reaction, right, it is independent on the concentration or partial pressure, but it is dependent on the temperature. So likewise, Kc and Kp will be a constant at a specific temperature, but it will change when there's a change in temperature. Can? So you must remember that Kc and Kp is a constant. It is not affected by any change in concentration and reactants of the reactants and products. It is not affected when you add or remove any reactants and product. Kc will be a constant value. It doesn't change with pressure. It doesn't change with partial pressure. It doesn't change with the presence of catalyst or the absence of catalyst. Alright, so Kc only changes. So you must remember Kc or Kp only changes with temperature. Can? So this is just a summary of what we have discussed so far lah. Okay, so